Yeah, so this is the fourth lecture, and so we have spent maybe the first two lectures of this course to learn about what factorization algebras are. And then in the third lecture, I talked about what constructibility is. And so unfortunately, the organizers only gave me 4 lectures instead of 5. So I will leave it as an exercise to ponder what off means. And so we'll skip straight to assembly for the fourth lecture. So assembly is basically the question, how can one describe or maybe decompose, or maybe assemble from, decompose the data of a, let's say, constructible factorization algebra in terms of some simpler pieces. Or, of course, same question after the reverse. If we have some simpler pieces, what does it take to assemble them all together into the data of one big factorization algebra on some conically smooth, on some smooth conical manifold? Okay, and today I will introduce 3 main concepts which allow you to do this, and I will first start by telling you what they are. Then I will spend some time showing you what you can do with them, and then I will, towards the end of the lecture, if there's still some time, I will go a little bit into the arguments for how we would prove this. So let's start with the first technique, which is about gluing. So here we have the following theorem, so there's a version of this of Matsuoka in the locally constant case, so for ordinary smooth manifolds, and then the general case is one of the main results in our paper. Maybe the reason we started to write this paper to begin with, which says the following. I think I already mentioned this in the discussion session last time, but of course I should write it properly. So the factor that goes from the opposite of opens to cap infinity, and which sends u to factorization algebras, constructible factorization algebras on U, and the functoriality is with respect to the pullback, or just over restriction onto smaller opens. The claim is that this is a sheaf of infinity cachets. And so explicitly, what that means is that whenever we have U some open cover of X, or of course, let's say of X on V, then the category factorization algebras on V, constructible factorization algebras on V, admits a natural map, which then becomes an equivalence to the limit of the categories of factorization algebras of the I's, where here I ranges over the finite subsets, finite non-empty subsets of this indexing set beta, and here ui is just the intersection of all the ui for that specific big I. Okay, so this is part number 1. This basically tells you that if you have a manifold and you can decompose it, or like you can cover it by some things, this can be infinite cover, or sometimes maybe just a very small cover, then you can compute the value of the category factorization algorithms in terms of the value of the individual opens. Then we have the second statement, which is adductivity. So this is the question about how does the category factorization algebras behave on a product of smooth manifolds or smooth conical manifolds. And so this is not yet settled in full generality. So instead, this is still conjectural. So we write this as conjecture. And it's basically the obvious thing. If you have to make one guess, well, that's the one. So the claim is that constructible factorization algebras on a product should be the same as constructible factorization algebras in constructible factorization algebras, or of course the same the other way around. And so in order for this to make sense, one needs to have a symmetrical nodal structure on this. And I will say something a little bit later, how one can explicitly using Rune construct such a symmetric nodal structure. Of course, using the localization thing I explained last time, to identify these for just algebras for this localized opera, they're just algebras for some opera, so you will get a symmetric nodal structure by what Rune explained. But using the gluing, one can also construct a symmetrical nodal structure very explicitly. I will say this in a moment once I've stated the three things. So let me comment a little bit on the status of this conjecture, as far as I know. So as far as I know, in the locally constant case, there are two things that prove a version of the statement in the locally constant state. One is the same paper by Matsuoka, and the other one is in the PhD thesis of Eric Berry. Yeah, so unfortunately, I think Eric Berry left math, if I understand correctly, and so his PhD thesis hasn't been published yet. But I think I know he's a student of David Ayala, and I think it's supposed to at some point be published. And then in the general case, this is still a working project. By Anya, who was here. And as far as I know, some parts of this project are also joined with Victor Carmona. Correct me if I'm wrong on this. Okay.
In the part one, your X should be a stratified manifold.
Yes, I should have said this from the beginning. I probably should have said this. So for this last talk, all our spaces that appear, they're all smooth conic manifolds. And in fact, we even assumed that they have not good disks. So there exists a factorizing basis of this. So this will be our standing assumption. Thank you for reminding me. I should have said this before I started writing.
But the open cover can be anything if not the compatible. Do something compatible with disks in your sheaf.
Say it again.
For the sheaf condition, you can have any open cover.
Yes. This is an arbitrary open cover. It doesn't need to be a factorizing cover or anything like this. So it's really the standard sheaf condition we would write down. Yes. Okay. And then the third thing you need. So if you look at these two things together, let's say you start with a smooth conic manifold, and then the gluing tells, okay, you can decompose it into smaller pieces. But then if you know the basics that appear, like the local neighborhoods in a smooth conic manifolds, they're not as simple as they are for ordinary manifolds. Because locally, they all look of the form. They all have neighborhoods of these forms where we have some cone comes out in. And then using the additivity, you can split this into two pieces, the Rn part and the cone part. And then sort of you know what to do with the Rn part because this will be some Yen algebra. And so the last remaining question is what to do with these cone parts. And this is the third part of the ingredients one needs for this assembling. Which is the behavior of cones. And here we have the following theorem. So there's a version of this by Graf and Rosenblum. So they do this fully on the localized side using some multiplicity arguments, which maybe if I get to, I can do a very brief sketch, and then we will also put this independently. And so what's the statement? We have to be in a situation like that. So the Rn component, we can forget about it, but so we have to have some Z, which is compact. We can, of course, smooth conic manifold will not exist. And then the claim is that you can look at the following. So you would like to understand constructible factorization algebra on the cone of Z. And let me draw a picture here. So you have the cone of Z, which looks something like this, where Z is this represented by this vertical line. And one thing you can do, there's an embedding into here where we just forget the cone point. And of course, away from the cone point, this is just Z cross the open interval. But then what you can also do is you can project down. So the way I drew it is sort of just project horizontally down onto a half open interval. Like this. And then, of course, similarly here, you can project down onto the open interval. And this includes into here. And this square, by taking push forwards and restrictions, will give rise to a square that looks like this. So you will have a factorization algebra on this product. So this is given by restriction. And then here you can do push forward on P. And here restriction. You push forward 2. And the claim is that this square commutes and is a pullback. So in other words, if you look at what is the data of a constructible factorization algebra, in other words, so if you have the data of a constructible factorization algebra, it amounts to two things. So first of all, you need to have, let's call it B in the factorization algebra on this interval, and using additivity, this is the same as an E1 algebra. This is using additivity already. It's an E1 algebra, that's the 0,1 component, in factorization algebras on Z. And then the second piece of data you need is you need to take this push forward along here. And so I didn't explain it in generality, but this push forward will, and it's easy to show that it will send constructible factorization out of constructive ones, so it's well defined like this. And so then this push forward, I will denote it by integral over Z of B. So because basically you're integrating away the Z direction, and this thing will now still be, so this is still the E1 algebra. Because you integrate away this other direction, you're left with an E1 algebra, and you need a module for this E1 algebra. Because if you look at the data down here, this are E1 algebras, and constructible factorization algebras on this half open interval are exactly pairs of an E1 algebra with a module. So here we use that. Sorry for switching a little bit back and forth between the two boards.
I think Jonathan likes this job.
This is the forgetful functor that assigns, just forgets the module. Okay.
So this push forward, if I don't say constructible, I have this for just all maps?
Yes, exactly. So I didn't say this in a lot of detail. So push forward always exists on a level of factorization algebras. in general, if you push forward something constructible, it won't be constructible again. There are some criteria for when this is true. Yeah, it's definitely, this is just a product projection. This is like a very easy type of thing where it's always true, and you can use some other criteria, but yeah.
And then generally, if I have some kind of Haugseng square, I expect to get a commutative square at least.
Yeah, well, I would expect something like this, but I don't know a full general version of this statement. Yes, there should be some sort of nice interplay between this forward and backward functionality. And I would like to have a coherent version of this, but so far this is all very naive.
But the push forward is not adjoint to the restriction.
No, also because they live on very different things. Like the restriction is only for open embeddings, and the push forward is for some other class of maps, which includes these sort of projections, but is a bit bigger, and one can sort of give some examples. I don't know of a full characterization of the class of maps for which push forward preserves contractibility. Okay, so let me stay on this word and give an example of this, of how you would use these three things. So let's do a very simple example where we take S1 stratified with a single point. So the picture looks something like this. This has a single zero-dimensional strata and then a one-dimensional stratum like this. And then what you can do is you can first use gluing. So gluing will tell me that if I take the upper and so everything except the lowest point and everything except the highest point, so we'll get factorization algebras on this one, and then factorization algebras on this one. And then the induced map here. Okay, there should be like a fact everywhere. Yeah, I won't write it. So then here, this is just R. So here we know we just have V1. And here we have two copies of V1. And if you look at what this map does, so here the algebra goes around like this, and let's say I choose the same orientation like this, then if you have your associative algebra, then on one side it will have the same orientation, and on the other it will exactly reverse. So you will get the pair of A of and A. And so by gluing, the value here just consists of this such degree on here. So then the question is then we have to further decompose. We further have to decompose this, and this is just a cone. So this is just a cone on S0. And this is then exactly S0 times the open interval. So we can just put that square there that we already have. So this we can project onto the open interval, onto the closed interval. So now I draw it vertically because the projection somehow identifies these two parts. And here I have let's put the arrow just so that we can see how it goes. And then we will have a pullback also here. And then if you look at what this does, so here the value in sub open will just be the tangent product of the values here. So this pair will just go to A of tensor A as an algebra. And so then the total conclusion we get is that the factorization algebras on S1, they just consist of, first of all, only one algebra, and then a module for this developing algebra is called. Sorry. Like this. And in fact, the very same computation works in all dimensions. So more generally, you will get that factorization algebras on Sn with a single point will be pairs of an En algebra together with, so you take this N algebra and then you integrate away a full sphere of dimension Sn minus 1. And then this thing will be left with an one algebra structure, and you will need a module for that. And like the computation is exactly the same as if you use same thing in higher dimension. So this is an example of how you would combine these two statements. And I guess implicitly we're also using additivity. Yeah, I guess maybe not in this smallest dimension because it's just, in this case, it's just a co-product, but in higher dimension, you will probably implicitly use additivity. Okay, so let me now show you some more global statements on how one would maybe now use this to describe factorization algebra on manifolds, or on conical manifolds. So this is the following construction. Which I'll call link to composition. And basically the goal is to reduce the data of some factorization algebra to locally constant factorization algebras on the various strata, plus some data that will resolve. Okay, and so here's this is some sort of inductive procedure, and the key step is the following. So let's say we have X as usual, so X is above, and then let's say D is the minimal dimension of strata that appear in D. Very nice. I will make an example in a moment. So, and then let's say we have S. This is the union of all the strata of dimension D. It's like all the lowest dimensional strata in the manifold. And so then there's the following fact one needs to know about conical smooth conic manifolds, which is that S sits inside X and has a trivial neighborhood and this trivial neighborhood, so let's just call it T. This trivial neighborhood, it projects back down to S, and this forms a bundle, possibly non-trivial, but yeah, forms a bundle whose fibers so let's say we have a point in S, then what's the fiber? The fiber will just be or the cone on Z, where so this S is a point in original manifold. So this S, it has a local type. So its neighborhoods will be of some type D something something, and they will be of some type DZ, comma, and we know what the number is, because the number is exactly going to just be the dimension of S. And so the fibers will be just cones of this dimension. I will just cones on Z. So let me draw a picture so we can see what's going on. So example. So let's say as a stratified manifold, we take the Möbius strip, the open Möbius strip, where we do this to this, and let's say we have it stratified where we have an S1 in the middle. So this is like X, S1. So it has a one-dimensional stratum and a two-dimensional stratum, and this S1 is then just S. And D will be 1 with this one-dimensional stratum here. And then in this case, the trivial neighborhood is just going to be the whole manifold. So T is just going to be X itself. And the projection is just the usual bundle onto the sphere. And you see that the fibers, So the fibers, they exactly look like intervals with a point, which is exactly the cone on S0. And in fact, if you look at the local type around some point, the local neighborhood, it always looks like cone and 0 times this r direction. And yeah, and you see that this is a non-trivial bundle. Yeah. And then we also have a bundle which I call the link bundle. In this case, the one-dimensional link bundle of X, which projects onto S, which is just a bundle of which over S and S is just the Z itself. So not the full cone, but just the Z itself. You can, for example, view this as a sub-bundle in this bundle, so just choosing some distance, and then in this case, it will be -0 bundle. Okay, so this is the ingredients we need. And now using these ingredients, let's see. So using these ingredients, we now can do the following. So we have this cone bundle. So this is the bundle, and I will also show what happens locally. So pointwise, we of course know it's just S, and then it's going to be some cone, and then we can form a bundle onto V where pointwise we do this projection at P, which takes the cone and projects it onto the ray. And so we will get a bundle D, which is the associated ray bundle. And note that this V is in fact a trivial bundle, because there are no non-trivial self-diffeomorphisms of this stratified manifold. So this will be a trivial bundle. And so we can now put all of this together, and we can look at the following diagram. We have V maps to V, and then we can remove the zero section of the tubular neighborhood, and we can remove the zero section here. And since this is a trivial bundle, it is of course just S cross 0, 1, and then this is just S cross 0, 1. And so locally, so whenever you have a U sufficiently small in S, so S is the lowest stratum, so it's really just an ordinary manifold. So the local opens will just be some R to the D's. And if you look at this picture locally, it will be something you recognize, because so there will be some RD, and then the T locally is just a cone. The T without S, that's just the cone where we take away the cone point. And then this is just what's written here. Sorry, and yeah, exactly. And then locally over S, this is just the half open interval. And this is just the and I guess I probably should have drawn these maps the other direction. Of course, we will then pull back along them, but on the level of spaces, I probably should have written this direction. Okay, and this is a picture we know, and this RD component, we can ignore it because by additivity, we can split it off. And so all this together says that using additivity, using the cone description, and using gluing. So basically, locally, you know what happens. then you cross it with RD, and then you glue it together along all these U's. And here you can really choose. So since it's an ordinary manifold, you can really choose a cover of U's by things that are RDs, such as both intersections are again RDs. And so all this to say is that when you put all of this together, you get a pullback diagram like this. You get a pullback. I will draw it below, and then there will be one more thing coming above. So this just says that factorization algebras on T are just the same as saying you have one on T without S. And then and then one like this. And this will be a pullback. But of course, this you can also simplify further. These are just respectively, this is only one, again by additivity, this is the one algebra in factorization algebras on S. And now S is just an ordinary manifold. So I don't even have to write constructible anymore. This is really just locally constant. And then similarly here. Like this. And then up here, we can do one more instance of gluing where our original manifold, X, it of course had an open cover, but where on one hand I take T, that's distributed in the neighborhood of S, and on the other hand, I take everything that is not S. And then again, by gluing, there will be one more pullback square on top. And now, if you look at what we achieved, we've seen that we started with our manifold, and we described it in terms of three pieces, where these and these are just algebras and modules in some category of just factorization algebra of an ordinary manifold. So this is just a locally constant thing. And then this guy, we got rid of the lowest dimensional stratum. So if X had a lowest dimensional stratum of degree D, this new thing will have the lowest dimensional stratum of degree D plus 1. And so by iterating this procedure, you get the following picture. So now if you have a general manifold, I mean general conically smooth structure, etc., like with the same standing assumption, but not with this degree D yet. So by iterating, you get the following sequence. So you have factorization algebra on X, and then you can keep splitting off all the lowest dimensional stratum one at a time. So okay, so the first step, you go to factorization X of X bigger or equal than 1, where here I will use the notation that X bigger or equal than n. This is the union of all strata of dimension bigger or equal than n. And so in the first step, you split off the zero-dimensional strata, then you split off the one-dimensional strata, and so on. So you have a sequence like this, and the sequence will terminate if the global dimension of X is finite, which of course often it is. It doesn't necessarily have to be, but I guess in many cases of interest it will be. And then each of these, you can say a lot about it, because what you will have is you will have a pullback square, which is just the composite pullback square here. We'll have a pullback square where this thing will just be a Cartesian fibration that very specifically looks like it's going to be E1 algebras in something, and specifically it's going to be E1 algebras in the locally constant algebras on the n-dimensional stratum of X, and then this will be our modulus on something. And again, on the same n-dimensional stratum. So here I guess I should put the notation. Xn is the n-dimensional strata. That's the union of all the n-dimensional strata. And so this is a Cartesian fibration because it's just right modulus over an algebra. And so by pullback, this will be a Cartesian fibration. And the fibers are all some module categories. So this gives you some way of getting a handle on what factorization algebras are in this sort of inductive way. Is there a question?
Yes. You said this S has minimal dimension for the.
Yes. So the S minimal dimension, we use it so that this the tubular neighborhood exists. And so this pullback only exists if S has minimal dimension. But then here we're just sort of successively, like the S will change every time, like okay, let me say. So we start with X here. And so we start by splitting off the things of dimension 0. That would go to here. And then we start splitting off the things of dimension 1 and so on. And so every step, we're using this thing we already proved, where at every step you split off the things of minimal dimension. Okay. Good. So then, yeah, one more application, or something I should definitely say, it has to do with the symmetric monoidal structure. And this is like a very silly application because we're only using a very trivial instance of gluing, but nonetheless. So this is a symmetric monoidal structure on constructible factorization algebras of X. And it's just, you can just get it as follows, where, so let's say we want to define the map from here, the tensor product map to here. Then what you can just do is you can look at the category of factorization algebras on X disjoint union X. And then you have the two restriction maps, and by the gluing, this will be an equivalence. And then here, you can take push forward along the fold map. And again, this is one of those maps where the push forward preserves constructibility. And so this gives you a tensor product. And I mean, from this description, it's pretty clear how you make this into a coherent one. You just sort of define a Siegel object, where at the value of n, you just take factorization algebra on n copies of X, and then this will just be the Siegel map. The Siegel map will then always be improvements.
So constructible factorization algebras is a full subcategory of open tensor algebras. Right?
Open, yes.
And that has a symmetric monoidal structure.
Yes.
And this is the restricted.
Like
it's kind of pointwise, it just tensors the values on every that file. If not.
Yes, it is. It is. It is that. That's right. Because if you compute what it is, if you take an open, you push forward things, you have to take its preimage. Preimage will just be 2 copies of the open. And then the value of the blue factorization algebra, since it's multiplicative, will just be the value of one tensor the value of the other.
Okay.
So it is just, so this is indeed just the one you get by restricting the pointwise one. This is something I will I maybe should mention, this is a question I have to which I don't know the answer, which is there an analogous tensor product on just factorization algebras without the constructibility? And the problem is basically the same problem that I explained last time, where I don't know whether it's true, and probably not, but I don't know, that if you have a factorization algebra on a disjoint that the Weiss condition on a disjoint exists. Okay.
You can't even build a factorization algebra on this union by gluing two on the pieces.
Exactly. I don't know how to do this without constructibility. Yeah. It's exactly that problem. Yeah. Of course, you can build a pre-factorization algebra, but then I don't know how to show that it satisfies the Weiss condition. Yeah. And one more remark about this is that all these statements that I wrote on the board before, like for example, the gluing can be upgraded to say that this functor here is a sheaf, not just of category, but of symmetrical nodal categories. With this symmetrical nodal structure. Okay, so this is more or less everything I wanted to tell you in terms of the content. So now is maybe a good moment to ask questions. If once we're done with that, I will spend the last 10-15 minutes giving some ideas about how you would use the things I explained in the last lectures to prove the gluing and cone decomposition statement. But so maybe now is a good moment if there's some question. Maybe I will wipe the board if you can come up with questions in the meantime. Yeah.
If I have a reasonable infinite dimensional stratified manifold,
Yeah.
Is factorization algebras on constructible factorization algebras on that the same as taking the inverse limit of giving it on each of the n-dimensional things?
I'm not sure about this actually. Yeah. I would honestly expect more the opposite, where so you have whenever you have X, you have this system where you take away strata at the bottom more and more. I know this is also definitely not going to be a limit, a co-limit. So no, maybe it should be some sort of inverse limit, but I don't know. This sounds like a very reasonable question, but I didn't think about this.
Well, you have introduced this link once.
Yes.
And you don't seem to have used it.
Yes, I guess I didn't. I guess the link one appears if you explicitly want to say. If you explicitly want to say what this map here is, it's going to be you have a factorization algebra on here, and to get a factorization algebra on this stratum, it's gonna be integral over link. I guess now this is no longer link. So I should have called it link D. I should have called it link D because the D's that I mentioned. Okay, D was one in the example. That's why I called it one. In general, it's link D, which means here it's link N of Xn, I guess. So Xn is the n-dimensional stratum. It has some link. And if you integrate A over that link bundle, that will give you this thing. That's why I wanted to have the notation, but it's not important, and I forgot this.
If you restrict X to this link N, will it be also an E1 algebra in factorization algebras in the link? So then what
So you cannot restrict A to link N because link N is some lower dimensional thing. So yeah, this notation is maybe a little bit confusing. Let me give you the example of the Miller's thing again. So if you have an algebra here, then in this case, the link bundle is this S0 bundle. So the link at every point is just S0, and the link bundle is just so the link bundle is going to be the link 1 bundle at S, where S is just S1, is going to be the non-trivial, it's going to be a non-trivial S0 bundle over S1. That's the link bundle, and it doesn't make sense to restrict the factorization algebra on this because this is some lower dimensional thing. It's more like you integrate away this direction. So what you do is you take your A, you restrict it. So you restrict it to this two-ball neighborhood. This you can do because this is open and everything. And then this thing is locally equal to this times, or I guess that what I mean is that there's a projection map. No, locally this thing is link. Locally this is cone on the link. And then this map down here is just a push forward along the map from cone on the link to 0, 1 to 0, 1. Yeah. Sorry. Okay. This is on the left side. Okay. So yeah. Okay. Yeah. Okay. Let's do it super locally. If I have just a point S, then locally the picture is this. Z would be the link. And then the push forward I'm talking about is just push forward along this map. Yeah. And then it's the same as like global, but it's a bit harder to think about this. Okay, sorry for getting a little bit confused here. Are there any other questions? Okay, then I will give a brief sketch of how you would prove some of the results I mentioned. Okay, actually I will erase this again because I want to draw a big diagram on this board now. So let's talk about proving. And so we have a cover UI of X, and whenever it's relevant, I'm just gonna, without loss of generality, assume that it's just we want you to just to make something a bit easier to write. Okay. So what do we have to compare? On the one side, we have to take the limit of factorization algebras on these U's. And then at the very other side, we would like to say that this is the same as factorization algebras on X. Okay. And we can, let's recall how all these things are defined. So factorization algebras, they are just, so first of all, I can forget about the constructibility. Then I can also forget about the Weiss condition. Then I just have multiplicative algebras for the operand. And then I can do the same thing where this is something I discussed when I was talking about multiplicativity, is that one can always get rid of the empty set. This is in fact even going to be equivalent by what I explained last time. And then finally, one can forget about the multiplicativity. So this lives inside just living alg for this thing without the empty set. Okay, and now we can try to work ourselves up from the bottom, and we're going to need the following notation. So I'm gonna write U down. So this is the I had it already in the very first lecture, but just to remind you, so these are all opens in X such that there exists some U in U that contains them. And then I will use the same notation with an underline for this without the empty set. Yeah, this thing with the empty set, it's not a big problem. This is just a small technical issue that I don't want to lie about, but I also don't want to talk about it too much. Okay, so the first thing you do is you have a comparison map really just on the level of algebras for this operand. And so the step one, so let's say one, is to show that this is an equivalence. And in fact, we even show very directly that these operads, of which we're taking algebras here, are just columns. So let me just write it for this simple color with U1, U2, i.e., we have a push out of infinity-operads where you have U1 without empty, U2 without empty, then the intersection without empty, and then this the things that are contained in one or the other. So you have a push out of infinity-operads like this, 10%. And this is almost tautological. If you work, for example, with dendroidal sets and probably with dendroidal spaces, you can do something similar, just because this is really just the union of these two, and every operation here exists either here or here. So this is really, for example, if there's a model catching on dendroidal sets, and this will just be a strict push out where everything is cofibrillant, so it's going to be hard. And the reason we're removing the empty set here is because otherwise they're not cofibrillant, which is kind of annoying. It doesn't make a big difference. Okay, so step one says that you have an equivalence on the level of these algebras. That's just a computation of the operads themselves. And now you have to somehow work your way up. And so the first thing is you show that this equivalence restricts to an equivalence on the multiplicative things. And then here, this is the thing I explained last time, that here, the difference between here and here is just removing the empty set. But we saw that the empty set carries no information in the multiplicative case. So here you can just remove the empty set. That's for these ones. And then here, you now have factorization algebras on this, which still sits inside here. So now we have to check the Weiss condition and the constructibility condition. And this is very easy. So here, this is basically due to the fact that every instance of the Weiss or of the constructibility condition is something about you have some open and then some smaller opens than it, but every instance of such a thing will already fully take place in one of the UIs. Because the only opens that exist in here are the ones that are somehow subordinate to one of the UIs already. So this is really just easy, showing that it restricts all the way here. Okay, so far so good. Now you've extended from this limit of opens to this, but this is still pretty far from the thing we want, because here we only have opens that exist somewhere in some of the UI. But now this is where we can do two steps. So first of all, we can do disjoint union completion. So now we use the two tools that I introduced in the second lecture, where here we have shown that on multiplicative algebras, whenever you have something that's decomposable, you can add disjoint unions. So this will be an equivalent, this is disjoint union completion. And now you would really like to say that it restricts on equivalence here, but this is exactly that annoying thing that I don't know how to do, which is about establishing the Bayes condition for this disjoint union completion, which means that we have to wait for a moment. But luckily, when we go all the way to constructible ones, there one can now still show that this induces an equivalence. And this uses that thing I also explained last time, which is about the fact that in the constructible setting, you get Bayes for free on disks, essentially. So it's a bit small. In the constructible setting. But this was one of the theorems I explained last time. So luckily we can somehow skip this one step in the middle that I don't know how to do. And then the last thing is easy, well, it's not easy because it was some amount of work, but using the thing I explained last time, now we observe that this guy is now a factorizing basis of X. Because it's obviously a basis, because by definition the U cover X, and so if I close it downwards, it's a basis. And the fact that, and it's obviously closed under intersections because it's not just closed downward, and we've added in this disjoint union, so it's a factorizing basis now. And so by extension from a basis, we get an equivalence here. And then finally, this will restrict an equivalence here. And here you need to know that if something is constructible on X, you can know that it's constructible on all these. But that's exactly the statement, or very closely related to the statement, that constructibility is a local condition. Which was also one of the things I introduced last time. And so overall, if you take all of this together, you get pretty long. Okay. Yeah, I think I will stop here, and thank you all for your attention. Yes.
Yeah, to follow up on my previous question. So if you take this tubular neighborhood T, then T minus S should be something like the linked bundle
Times
0, 1.
Yes.
And then is it correct that if you restrict you can restrict the factorization algebra on X minus S to this guy,
Yeah.
and then use what is it called, additivity?
Locally, it's additivity and including. So I don't think this will be. I'm not sure if this will be globally trivial. This bundle.
No, but the factor 0, 1 is. So I can interpret this now as an A1 algebra.
Yes.
Factorization algebra over the link.
Yes, that's right.
And then integrating, it returns me an A1 algebra.
Yes, that's right.
Is this what up?
That's right. That's right. I somehow. Are you sure that this is trivial, that one can pull out the 0, 1 direction? If this is true, then yes. No.
But because it's a radial coordinate, somehow it should be. How far you are from S?
Okay, I think I will have to think about this, but if no, that I don't. I don't think this is trivial, right? Like in the example of Olympus. Yeah, it is. No, you're right. It is 0, 1 times, and then the S0 bundle is non-trivial, but you're right. It is. It should be a trivial bundle, and so then you can pull it out. Yeah, so that's one way of describing this push forward globally. Yeah, that's right. You have to first restrict it to this complement, to this tubular neighborhood minus the 0 section, and then project away the radial coordinate. Sorry, project to the radial coordinate. Yeah. Yeah.
What's the most exciting stratified, smooth stratified space that you've thought about?
I mean, the ones I think about in practice are usually rather simple ones, like some spheres with some stratifications. Yeah, usually that's so not that exciting.
And I guess maybe I've already asked you this actually, but like, what if I take a knot in R3?
What do you
Can you
do?
do something with the fact that you get a factorization
Factorization
on like, sorry, on the stratification of I have a knot in R3 and I stratify R3 by the knot being a stratum and the rest being stratum.
See,
it's like this should know something about knot invariants.
I have no idea. I've never thought about this. Yeah, maybe. Yeah. Okay.
Yeah, another question. So if you take a stratified manifold, you can refine the stratification, say by taking a smooth stratum and anyway subdividing it in more cells.
Okay.
Is there a comparison between factorization algebra with respect to the two stratification, possibly of the form one category of factorization algebra is the subcategory of the other where something is local enough?
So let me just make sure I understand what you're asking. So you're saying, like, for example, I take R, and then I can take the same thing, but like with an additional stratification? Yes. So then, yeah, because then, I mean, factorization algebras here will just be a full subcategory of the ones here, where you have, so because the constructibility condition here will just be a weaker condition, because you have less, like every inclusion of disks, every inclusion of stratified disks here of the same type, when you make a stratification, when you remove strata, it's still gonna be the same. And so everything that's constructible here will be still constructible here, but not vice versa, and so it will be a full subcategory. It's just more, there's like more disk inclusions here that have the same type, because everything has the same type, and here, yeah. I don't know if this was what you were asking.
Yes. Right there.
Yeah.
Which I guess you could think of like subdivision is an operational factorization algebras.
Yeah, exactly. It is true. It's one more operation, which, yeah, I mean, on factorization algebras, these are literally the same, because just the notion of factorization algebra makes no difference between, I mean, the notion of factorization algebra itself only cares about the underlying topological space. The only thing where they differ is the full subcategories of constructible ones will be different. Because here you will have less conditions than here. Yeah.
So the fact that the vice condition, like, it's unclear if it even pig blue on a distant medium, I kind of suggest to you that maybe that is not like the right condition to push for factorization.
Maybe. I'm open to be convinced that
Nobody has proposed anything else.
This is the one well, so the ones I know are the vice condition, the vice hypersheet condition, but I don't know if that makes it better for that specific question. Yeah. Maybe there are some better conditions someone can pose that.
You get some examples of non-constructible factorization.
Yeah, it's not so easy to come up with examples. And yeah, it would be nice to just come up with a counterexample to this thing about the disjoint union, because then one could at least say, okay, this is what goes wrong, and then what we.
Yeah, are all the examples that are still on William look at constructible?
I don't think necessarily, I don't think so. I think, but to be honest, I also don't understand a lot of what they're writing about this, because it has a lot of input from physics and like some stuff that I don't understand. So I'm not so sure. Like I'm qualified to comment.